All right. So for this lecture, we're going to be touching on a different type of junction than what we've covered so far, which has been semiconductor liquid junctions and then semiconductor metal junctions. And then we're going to get into some of the non-ideal behavior that can happen when you're working with a real system. So the type of junction that we're going to touch on is the p-n junction. So it's a junction that's formed between a p-type and an n-type semiconductor. It's a solid state junction. You don't really form these in liquids or gases or things like that. And as you might expect, it's what happens when you put a p-type semiconductor and an n-type semiconductor together. So in this case, I've got my two semiconductors here. Here's my n-type and here's my p-type. And what we're going to do is we're going to put them together. Now, this is a super important type of junction in industry. It's how basically all solar solar panels that you'd see on a house, it's how essentially all of them work. But it works pretty similarly to how what we described before. So just like in a liquid or a metal contact, the carriers are going to diffuse across the interface because of a difference in electric potential or chemical potential, because look, our Fermi levels are not equilibrated. And they're going to keep diffusing and keep building up an electric field until everything is nice and equilibrated and there's no net charge transfer. The difference is that for a p-n junction, we now have similar numbers of available states. Now, if you recall in, say, our semiconductor liquid junction, we start here. We have our Fermi level there, Fermi level here. In this junction, we have like tons more states here, right? If you were to look at, say, like because we're in the metal conduction band, or if we're looking at a liquid, like we have a concentration of, species that's like 10 to the 8 times larger than the number of carriers that we actually have, right? Our number of dopants. So because of that, because we effectively do not change the concentration of any of the species over here, we don't fill up the space, the number of states appreciably. If you were looking at a semiconductor metal contact, you're comparing a dopant concentration of like 10 to the 16 maybe to a metal concentration of conduction band states that's like 10 to the 22. So again, we're talking like 10 to the 6, so like 1,000,000 times more states over here than over here. So what that means is that the only thing that really changes appreciably is the number of states, number of carriers on this side of our barrier, or on that side of our junction, which is why we say that, okay, this Fermi level over here basically doesn't change. The one that changes is this one. It comes down, and it causes the band bending to happen. Right, so the bands bend on this side of the junction, where nothing really happens over here. So that only really happens for semiconductor, or for junctions where it's a pretty lopsided charge transfer, or it's a pretty lopsided number of states on one side or the other. One of the things that Nate is fond of using to explain this is, like, imagine you have like a can of soda, right? And there's a hole in the bottom, right there. And you bring that can of soda to the ocean. So we've got the ocean here. And then you try to fill it up to, let's say here, let's say you add in a number of charges, or you add in an amount of water that gets you up to here in the can. Okay, so what's going to happen is the system is going to equilibrate, right? We can't have this difference in potential here. So what's going to happen is water is going to flow out of our can. We have now an equilibrated water level, right? Everything wants to be nice and even here. Now, technically what happens is the water level in the can sinks and the water level in the ocean rises a little bit. But because the ocean is so much bigger than the volume of the can, this motion, this ocean like getting a little bit larger, is so infinitesimally tiny as to be irrelevant. Which is why we only really, so this is similar to what we're looking at for a semiconductor liquid junction or a semiconductor metal junction, where on the metal or the liquid side, the amount of water, as it were, is so much larger than what you would have inside the can, which is our semiconductor, that really the only charge transfer, in this case, like moving the water, the only charge transfer that really matters is inside the can or inside our semiconductor. So hopefully that makes a little bit of sense. But now this is like saying, well, instead of having an ocean, we're just going to have this way. Instead of having an entire ocean, we are going to now put two cans next to each other and fill them up a different amount. I'll put a little hole in between them down there. So now we are going to get charge transfer that's appreciable here and charge transfer that's appreciable on this side until they even out, right? That's kind of what we're going for with the PN junction. And so what happens is you get band bending on both sides, right? Because that transfer of charge, that difference in the concentration of carriers on either side, leaving those ionized donors or acceptors, right? Should have, so remember on this side, since we are transferring electrons out, we're going to have some positively charged donors on this side, building up an electric field, and there's going to be negatively charged acceptors on this side. Because in this case, we've transferred holes this way. All right. Okay. So that's sort of what this junction looks like. And because we have now these depleted regions on both sides, we have band bending on both sides. And if you were to draw a diagram of this, you know, just like before where we had, let's see, this is like our charge density. So this is charge density. So on one side, we're going to have this amount, and then on the other side, we're going to have this amount. And these should be the same area. So what could happen is, let's say that one of these is more highly doped than the other. So let's say the N type is less highly doped. So the P type, this side, is going to be more doped. You would get a thinner region here. Remember, because it has more states to accept those charges going back and forth. But you should still get the same area in between the two. Again, this works for the regular junctions as well. It's just that that area is so thin as to be ridiculously small. We don't care about it. Similarly, if you were to look at your E fields, for your electric field strength, it would kind of go up and up and up, and then down and down and down. And then if you were to look at your potential here, right, it's going to go up, and then it's going to, our electric potential is going to decrease, right? Cool. So the equations work just like before. There's nothing that's super fundamentally different about this other than the fact that the band bending occurs on both sides, and thus you have depletion widths on both sides. And since this class is about photoelectrochemistry, PN junctions aren't like super relevant. These are going to be mostly for solid state devices. So if you were to take like a material science course or solid state physics or semiconductor physics, these are going to be super duper important because, like I said, they're in like everything that you use a semiconductor for in industry, like solar panels and things. But for now, since it's not an electrochemical system, we're going to leave this alone. And we're just going to say that these junctions exist. They're very important. We now have a concept of how they work, right? And we should recognize when a PN junction happens. And we should be able to draw a band bending diagram, at least qualitatively, that would display the behavior of a PN junction. But I claim we're not going to need this going forward, at least for the time being. We'll touch on this again when we get into non-equilibrium systems. But for now, I think this level of understanding is okay. So we're going to switch back to semiconductor liquid contacts. Because we have so far looked at ideal systems. And now we want to look at one of the more important non-ideal cases. So we looked into this idea of barrier height, which we showed before is the difference between our conduction band edge and our redox level in solution. So if we switched redox couples, we should change the barrier height, right? So if we start over here where we have like redox species 1, we have some barrier height here between our conduction band edge and our redox level. But then if we go over here, exact same semiconductor. So the conduction band edge is in the same place. I think I got it like almost right. Yeah. But now we've changed our redox couple. So now its redox band edge is here. Now that's going to result in less band bending because it's a lower electric potential between the two, and our barrier height will decrease. Similarly, you could imagine a situation. We have much higher band bending, right? Similar idea. So in this case, we've changed redox potentials, we've changed redox species, and thus we have changed the barrier height. However, that doesn't always happen. That is for an ideal system. There are cases where you will change your redox species in solution and you do not change your barrier height. It's called Fermi level pinning. And the way that you would tell, obviously it's very difficult to just outright measure the barrier height of a solution. So what happens is you measure the VBI, right? And recall the barrier height is going to be equal to VBI plus V of n, which is a constant, right? So what's happening here is somehow we start over here with this situation. So we have redox 1, and we have, let's just say, this same VBI. Then we are going to change our redox species in solution. Let's make it more negative now. So R2 down here. But we measure the same VBI. So it looks like this system hasn't equilibrated, right? Because what happens is we're having the same voltage even though we have two different redox couples, which makes it seem like this Fermi level here, the one that's in the semiconductor, is pinned right there. right. Zoom cut out there for a second. So how do Fermi levels normally equilibrate? Well, we have two Fermi levels. And what's going on is that we're transferring charges in between our two species until we build up these potentials, right? So really the way that you equilibrate is by transferring charges in order to cause a potential drop so that the potential across the whole thing is equivalent. So what's happening here is that it seems like there's another species that exists here that is able to transfer charges. It seems like there's something in between our semiconductor and our liquid that is able to move charges around and is able to sort of like buffer the charge, buffer the differences in potential between the two. So what would that look like, right? Like it just means that there's something going on in here. There's some extra thing that we didn't know we put into the liquid that is able to cause this change in potential. It is able to absorb this change in potential, as it were. So frequently, these are from surface states. So there are states that happen at the surface due to the fact that if you look at the surface of a semiconductor, it is not the same as the bulk, which, might be like a very intuitive thing. But I mean, really think about it. Like the surface of a semiconductor does not behave the same as the bulk of it because the bonding is different, right? So for this example here with silicon in a bulk system, we have all the silicons are bound to 4 other silicons. Everyone's nice and happy. Everyone's got full bonds, but at a surface, somebody's got to lose. Somebody has to have a bond that's just sort of dangling out there. And so this is sort of where the science of surface chemistry comes in that like surfaces are super different. And these states are going to be electrochemically active, right? Just like any other bond. And in fact, they're often quite reactive because chemicals don't like to have bonds just kind of dangling out willy-nilly free to the world. So they can do all sorts of things. They will sometimes bind to species in solution. So they might bind to your redox species, or they could bind to your solvent, or to like your electrolyte, or your supporting electrolyte. It might bind to impurities in your solvent, all sorts of weird stuff. You might bind to, say, oxygen or other dissolved gases in your solution. You might form a surface oxide layer, or you might just reconstruct your surface altogether. What will happen sometimes is that this difference between here and here, this energetic difference is called the surface energy. And so what will sometimes happen is your surface energy is so high. In other words, it is so energetically unfavorable to form a specific surface that it is more favorable for your entire crystal to just start rebonding. And so you get like scattered bonds all over the place and you can reconstruct into a different surface. So let's say that for a specific semiconductor, the like 100 face is like super high in energy. And let's say the 110 is low in energy. So what might happen is if given the chance, your semiconductor surface will attempt to reconstruct itself into a 110 face. So it can be pretty complicated. And sometimes just other weird things happen. You'll have surface dislocations, you'll have different types of defects. All sorts of things can happen here at the surface. And when you do that, you form different species. You form like, so for example, this silicon R bond is not the same as a silicon-silicon bond. Neither is this silicon-oxygen bond. Or if we have this like new, let's say we have like a silicon bound like over here, you know, there's going to be some strain in this bond. So that's not going to be the same as a bulk bond. So the reactivities are going to be different. And sometimes, so we can actually, since the reactivities are different and band bending diagrams are essentially just diagrams of energy, what we can do is we can add those states to our band bending diagrams. So sometimes what will happen is these will exist within the band gap. So you get these intraband states sort of in here. So a lot of my undergrad work was working with nickel oxide, which is sort of famous. Oh, let me get rid of this. Yeah. So nickel oxide is sort of famous for its defects. So what would happen frequently when you synthesize a nickel oxide film is you'll have a nickel and then an oxygen, right? And then there's nothing. And then there's another oxygen and another nickel. So you get these nickel vacancies, right? And then these nickel vacancies lead to these oxygen dangling bonds over here, which cause things to rearrange. Usually you add like protons and stuff over here. Sometimes you'll get these, so you'll get like some nickel hydroxide. Sometimes you'll even get nickel oxyhydroxide if it binds to water. These states are notable because what will happen, let me erase this. So if we were to draw our band bending diagram for nickel oxide, it's a p-type semiconductor, so the Fermi level's down here. So we have some surface states. Let's say they're in here. So the band gap of nickel oxide is like 3 eV-ish. I think it's actually like 2.45 or something. It should be, so pure nickel oxide is like a light green color. Or like almost transparent. It absorbs mostly in the UV. But because these surface states exist right here, you can actually absorb light at a much longer wavelength, which means that it absorbs a whole lot more light in larger regions of the spectrum, which leads to defective nickel oxide being black. Right? Because it's absorbing all that, all the light that it's not supposed to. So that's just an example of how that can change things optically. And you can imagine if it's changing things optically, it's also probably changing things chemically. So that happens at our semiconductor surfaces fairly frequently. So the way we're going to draw this is we're going to have on our semiconductor over here, and then we're going to have sort of this region of the surface states. So this region, we're just going to draw as sort of a block because it's a little bit easier to visualize this way. And we're going to use this region as a way to drop voltage. So there's going to be like a set amount of voltage that you can drop across this interface due to the number of charges that, for example, are available to you. But this is going to be how we're going to do it. So as you can see at this point, everything's nice and equilibrated. We have our electric potential for our redox species. We have our Fermi level, and they look like they're in the same spot. Great. Everything's nice and equilibrated. Note that I don't actually draw anything in here. Okay. So now what we're going to do is I'm going to change the potential. I'm going to change the redox potential of this species here. Let me just double check. Yeah, okay. So what I'm going to do is I am going to try to bump this up a little bit. I'm going to change to a different redox species. And what I'm going to try to do is I'm going to try to shrink the barrier height, right? Which remember is this distance here. This is barrier height. And what I'm going to do is I'm going to measure the voltage. I'm going to measure the VBI right there. But if our surface states have the sufficient ability to balance all the charges, which means we can transfer charges between just the surface states and our liquid enough to balance out the difference in redox potential of our liquid, all of the potential drop happens at the surface, and it doesn't happen in the bulk semiconductor, which means that VBI doesn't change. So the voltage that we actually measure won't change. So what's happening here, you can sort of imagine this. So this is like how it used to be. It used to be flat, right? So you're going to just sort of pull this side of our band banding diagram down a little bit, or push it up, depending on what the case may be, such that, we have this change in potential over here between our two redox potentials. Well, we're going to drop all of that potential over the surface state right here, right? So the potential at the surface is going to drop enough that we are actually going to, just like normal, we're going to equilibrate everything. The Fermi levels are going to be at the same spot. We're going to have no net charge transfer. Everything's still at equilibrium, but we haven't touched the bulk. And because we haven't touched the bulk, this VBI here hasn't changed at all. So what that means is that it sort of looks like our Fermi level was pinned, right? It looks like nothing changed. So obviously this could be a problem if, for example, you wanted to make a device that had like 2 volts of potential drop, and then you measure it once with this one redox potential. You're like, okay, great. Now I'm going to change my redox species, and now I'm going to turn it from whatever it was before, let's say like 1.8 volts to 2 volts. So I'm going to add 200 millivolts to my redox species right in here. I'm going to change that. But then you measure it again, and it's the same voltage. Well, what that means is you have something going on your surface that is causing non-ideality in the behavior. Now, this goes up to a point, right? So if, for example, we manage to deplete all of these, we can, let's say, pull this down like to a certain extent. Eventually what will happen is you will deplete all of these states. So there will be like a certain amount of buffer that you can do. And then if you continuously increase the redox potential or decrease it or what have you, then you will start to get changes in VBI. Just what's going to happen, I pulled this up over here. If you had, say, a slope, if you were to plot here, so VBI this way, and E redox, what you should see is a linear slope, right? You should see a slope of 1. But if you're doing your experiment and you see, okay, it's 1 for a while, and then it just sort of stops, and then it goes back up again. So like this region here, where the slope does not equal, slope does not equal 1. That is an example of Fermi level pinning. But eventually it'll kick off again, right? It'll eventually you'll deplete all of your surface states and you'll be able to keep going. Okay, hopefully this serves as a nice introduction to both PN junctions and Fermi level pinning. At this point, we have constructed all the junctions that we want to construct. We have an idea of why they would behave ideally and why they would behave non-ideally. And now we're ready to start getting into the equations. So the next lecture is going to be pretty mathy. We're going to start deriving the ideal diode equation and applying it to some of these systems. I'll see you in the next lecture.